Today's video marks the beginning of Unit 2 in our course, which involves a great deal of graphing. We create graphs on what's known as the Cartesian plane, which is just a fancy phrase or name for a grid pattern using x and y values. The x values deal with everything horizontal, and the y values deal with everything vertical. For those of you that are historically inclined, the Cartesian plane was first introduced by a gentleman by the name of René Descartes, and has very, very many applications in maths, sciences, navigation, and even the arts. The Cartesian plane is made up of two axes, the x-axis and the y-axis. The x-axis helps us measure or keep track of any horizontal movement, and the y-axis keeps track and measures vertical movements. The origin refers to the point in the middle of the graph where the x and the y-axes intersect. Let's move horizontally to the right 8 units, and then move up vertically 6 units. At this point, no pun intended, we'll place a little red dot which we'll refer to as a coordinate. These two values, 8 and 6, help us measure the exact position of this coordinate. The values are always referred to in this order, the x value or coordinate first, followed by the y. They're separated by a comma and usually found in brackets, and together they are referred to as an ordered pair. In these examples, I've plotted a number of points. Now I want to label the coordinates for the point R. I move along 1 unit along the x-axis, and then I stop. There's no movement along the y-axis at all. R is right on the x-axis. So I label this point 1, 0. 1 referring to the movement along the x-axis, and 0 referring to the movement along the y-axis. For point K, I move 5 units along the x-axis and 4 units up the y-axis. So the coordinates for this point becomes 5, 4. For point P, I move 3 units along the x-axis and then down 3 units along the y-axis. Because I'm moving down the y-axis, I refer to this coordinate as a -3. So the point is labeled 3, -3. 3 to the right along the x-axis, down 3 along the y-axis. The point Q has no movement along the x-axis at all, so we refer to that as 0. But it goes down 5 units along the y-axis, so the coordinate for Q becomes 0, -5. For M, for the first time we're moving left along the x-axis, 6 units, and then down 4 units along the y-axis. Because we're moving left along the x-axis, we refer to it as -6, and because it's down, we refer to it as -4. So M is the ordered pair -6, -4. Finally, H is another 6 units to the left along the x-axis, followed by 7 units up the y-axis. So the ordered pair for this particular point H becomes -6, 7. We can refer to any movement along the x-axis as the run, and we can refer to any movement along the y-axis as the rise. If we connect the beginning of the run to the end of the rise, we get something that looks like a hill, and we'll refer to this as the slope. Now in math, we'll refer to slope with a very special variable, which is m. So anytime we're talking about m, we're referring to the slope. And the formula for calculating slope is rise over run. Now imagine you're walking and you come to a hill that has a fairly gentle slope. The top of the hill is, let's say, 20 meters higher than the bottom of it, and you get to walk 50 paces from the beginning of the hill to the time you reach the top. It's a nice, comfortable climb, not too strenuous. Now imagine you come to another hill. This hill is also 20 meters high from the bottom of the hill to the top, but you have to climb this hill in 10 paces, a much shorter run. Now if we connect the lines, you'll see that our slope has become much steeper. In this example, we have another slope here where the run is 16 units across and the rise is 3 units. Now watch what happens to the steepness of the slope as we maintain the same rise, but we shorten the run. You see that as the run becomes shorter and shorter, but the rise is maintained, that the slope becomes steeper and steeper. Now in this example, we're going to keep the run the same. It's still going to be 16 units, but we're going to adjust the value of the rise. Run remains constant, rise increases. And as the rise increases, the slope becomes steeper and steeper. The value of m becomes greater. Now let's look at some examples that involve numeric values for our rise and run. In this example, we have a run of 3 units, followed by a rise of 2 units. Given that the slope is measured as rise over run, we can say that our slope is equal to 2/3. Now consider what this means. For every 3 units we move along the x-axis, we move 2 units along the y-axis. In this case, up. In this example, we move along the x-axis 3 units, and then go up the y-axis 3 units. Our slope can be expressed as rise over run. In this case, 3 over 3, which is further reduced to 1. This means that for every 1 unit the graph moves horizontally, across the x-axis, it moves 1 unit vertically up the y-axis. In this example, our run is 5 units along the x-axis, then down 5 units along the y-axis. Because we are going down along the y-axis, we refer to the rise as -5. So now our slope is -5 over 5, or -1. This means that for every unit we move across the x-axis, we move down 1 unit along the y-axis. And if you run a line from the beginning point to the end point, you will see something that we refer to as a negative slope, which is why it's expressed as -1.